Welcome! This lesson is on electric field strength between charged parallel plates, which is a subtopic of uniform electric field and its effect on charged particles in Unit 18 electric fields. By the end of this lesson, you should be able to recall and use E equal to delta V over delta D to calculate the electric field strength of the uniform field between charged parallel plates. Describe the effect of a uniform electric field on the motion of charged particles moving parallel to the field. In the laboratory, a common way to get a uniform field is to charge a pair of parallel metal plates using a battery. A uniform electric field is a region in which the magnitude and direction of the field strength are constant everywhere. The electric field lines of a uniform field will be pointing in the same direction, parallel, and have the same spacing. The electric field always points from higher to lower potential. So, electric field lines are drawn perpendicularly from the positively charged plate to the negatively charged plate. The electric field between the plates is uniform, except near the edges of the plates. The separation between the parallel plates must be small compared to their length and width to minimize the edge effect. In the subsequent discussion, we will only consider the region near the center of the two plates, where the field is uniform. If the potential difference of the battery is delta V, and two plates are separated by a distance, delta D, then the magnitude of electric field strength between the two plates is equal to the potential difference across the two plates over the separation. Imagine two parallel oppositely charged horizontal metal plates. The separation of the plates is D. The electric potential of the positive plate is V1, and the negative plate has an electric potential of V2. A downward uniform electric field will be created between the plates. A proton with mass m has a charge, small q, is situated between the two plates. In a uniform electric field, the field strength is the same in magnitude and direction anywhere. So, the electric force acting on a proton is constant anywhere in the field. This constant force will cause the proton to move downwards with constant acceleration. The mass of a proton is very small, so the weight of the proton is negligible compared with the electric force. Then, the net force is the electric force acting on the proton. By Newton's second law, the acceleration is equal to the net force over the mass. And the net force is equal to the electric force. The electric force is equal to the electric field strength multiplied by the charge. The electric field strength is equal to the potential difference between the two plates over the separation between the plates. So, the acceleration of the proton is equal to the charge times the potential difference over the mass times the separation. And in this example, the potential difference is equal to the electric potential at the positive plate minus the electric potential at the negative plate. This equation is valid for the particles with very small masses such as protons, electrons. If a charged oil drop is placed into the space between oppositely charged parallel metal plates, the weight of the oil drop cannot be ignored. We need to consider the weight of the oil drop when calculating the resultant force. Imagine an electron of charge small q with mass m is released from rest at the negative plate. Then, the electric force will do work on it, giving it that amount of kinetic energy when it reaches the positive plate with a speed of v. The work done is equal to the charge of the electron times the potential difference between the plates. And the work done on the electron is transferred to the gain in kinetic energy. The gain in kinetic energy is equal to the kinetic energy of the electron at the positive plate minus the kinetic energy of the electron at the negative plate. The initial kinetic energy of the electron at the negative plate is 0. And the final kinetic energy at the positive plate is equal to half mass times the square of the speed of the electron at the positive plate. Rearrange the equation, we get the final speed when the electron reaches the positive plate, which is equal to the square root of 2 times the charge times the potential difference over the mass. The energy gained by the charged particles is small, and hence, it is convenient to introduce a new unit of energy, called the electron volt. When an electron with elementary charge E is accelerated through a potential difference of 1 volt from rest. The electric force will do work on it. The work done on the electron is given by the charge times the potential difference. Substitute the values into the equation and calculate the work done, which is 1.6 times 10 to the power of negative 19 joule. The work done is transferred to the gain in kinetic energy of the electron. So, the kinetic energy that an electron gains when it travels through a potential difference of 1 volt is 1 electron volt, and it's equal to 1.6 times 10 to the power of negative 19 joule. Let's try some examples. Please pause the video to try the question. Recall that the electric field between the two charged parallel plates is a uniform electric field. And the electric field strength is constant everywhere in a uniform electric field. So, the electric field strength at points X, Y, and Z are the same. The magnitude of electric field strength between the two metal plates is equal to the potential difference across the two plates over the separation between the plates. The potential difference is equal to the electric potential at the upper plate minus the electric potential at the lower plate, which is 2000 volts minus 800 volts and is equal to 1200 volts. It's given in the question. The separation between the plates is 4 centimeters. Convert the unit of the separation from centimeter to meter and substitute the values into the equation. Calculate the electric field strength between the two metal plates, which is 3 times 10 to the power of 4 volts per meter. The electric field strength at points X, Y, and Z are the same, so the option C is correct. We have come to the end of this lesson.